Good morning or good afternoon, everybody. Welcome to today's training webinar. Welcome back to those of you that have seen previous webinars from Quartzelec, and a special welcome if you've never seen one before. Hopefully you will enjoy this one. Now this one is a study of two particular generator failures, but it paints the picture of the problems that can cause generator windings to fail. Today's trainer is Wojciech Betlich. He's got many years' experience of dealing with customer problems with generator failure and with a particular interest in the windings and rotor design. Quartzelec's engineering team solve many customer problems and spend all of their time advising customers about their maintenance strategy as well. So if you have any questions about general generator maintenance, please feel free to contact us after this webinar. Now, before I hand over to Wojciech, I'll let you know how you can take a part in this webinar. The first one is by answering polls, which shall appear partway through the presentation. And the second one is by using the Q&A function. You can ask us questions, which we will deal with at the end of the webinar. So we'll spend some time after the presentation dealing with your questions. Okay, that's enough from me. Now I hand you over to Wojciech for today's training.
Thank you, Steve, and good morning, everyone, and good afternoon for those who are from far away. Yeah, we're going to talk about, well, the title of this presentation is Root Cause Analysis, Examples of Generator Breakdown. And what's better to learn from than real problems, real generators, and real data? We all agree that's probably the best way to learn, and we're going to talk about it today. But I'm going to start with that. So in June 1972, one of the domestic flights in the United States suffered from very quick decompression. And that plane was manufactured by McDonnell Douglas. The plane was DC-10. At the time, the door hatch has opened while the plane was 11 kilometers above the ground level. Luckily, that was the cargo door and nothing has happened to the people inside this plane. But what I want you to focus on for a minute is what the OEM, the manufacturer, has done at the time. He said that there is available modification to the locking system, but it's not compulsory. This is quite bizarre situation. And then, in a bit less than 2 years, in March 1974, yet another accident took place. This time, a lot more tragic, because nearly 350 people have died. That has happened in Europe, in Paris. And it was the same plane, McDonnell Douglas DC-10. And you know what bothers me the most in this little story? It is the fact that nearly 350 human lives must have been lost before an OEM has changed their commercial stand and started to implement door modifications and door monitoring system on every plane. Today, we know that pretty much everything is being monitored on planes. I can tell you more. Most, if not all, monitoring systems are redundant, just in case one of them fails. These days, safety of the passengers is priority, and an OEM cannot afford similar failures again. But before we move on to our case studies, let's ask one more question. Can generator OEM and generator manufacturer afford machine breakdown? I will let you think about it for a minute, and I'll try to answer that question at the end of our meeting. So if I ask that question, do generators have problems? For those who operate these machines, it's quite obvious. Of course, they do have problems. What the OEM, what the manufacturers do about it? Well, sometimes if there is a technical problem, inherent technical problem, they will send out letters. Letters that will tell you what the problem is and how to resolve that problem in the future. But it's just recommendation. It's not compulsory. So that is a resemblance between the generator manufacturer and the story about the plane we just said. So one of the problems the OEMs talk about is the slot partial discharge, stator slot partial discharge. And we will show two failures related to that problem. But before we do that, we have prepared a number of polls for you. And if you don't mind answering, because there's one question that coming, it should now appear on your screen. So before we move on, could you answer that question? Have you ever come across slot partial discharge? And the way how it works, I'm going to wait for another 10-15 seconds for you to vote. And I will reveal the answers to all of you. Okay. Now, let's see what's your experience with slot PD. Now you should see the results. So 60%, so vast majority of you have seen slot partial discharge. Then 28% said you haven't seen it. And then there's a small number, 12%, who said, I don't know. All right, so let's keep that in mind and let's continue with our training. So let's think for a minute about this problem that large generators will suffer from. What you see on the screen is the example of the slot cross-section of the stator. What you see here, and let me just find a pointer. There you are. What you see is the core, you have the stator wedge, then you have your top bar, and you have the bottom bar. And you can see clearly the difference between left-hand side and the right-hand side. The difference is when you have a loose coil in the slot, things can move. Obviously, you have magnetic components moving around. You have electromagnetic force moving these coils side to side. So if your stator slot is loose, you might end up with this problem. And on the left-hand side, you have nice ripple spring on the side, preventing that slot content from any movement. So have that in mind. Now, these stator bars will vibrate against the stator core. And we say that the stator core is nothing more than thousands of sharp knives that are constantly damaging your insulation. And this picture shows the slot section with the stator bars removed. And although when we manufacture stator core, we try this surface to be as flat as possible, it's never perfect. What it means that if your stator bar is moving against that rough surface, this is what you get. So you see examples of stator bars removed from the stator slot with a visible partial discharge on the surface of the stator bar. And then another good example. That's what happens when you have an air gap between the side of the stator bar and the core. Now, if you look closely into the surface of the stator bar where the spark erosion took place, there's something also called vibration sparking. So every time when the stator bar is vibrating in the slot, every time it stops touching the core, there will be a little spark going on. And when you look into the under the microscope, you will see there's a little ingress in that insulation system. And one thing that we need to remember about is that partial discharge is caused by the electric field. And the strength of the electric field increases rapidly when the surface isn't flat, but it's irregular. That's why if you have that spark erosion that you see on those two pictures, this is the best place for partial discharge and trimming to go and drill through the stator insulation system down to an air fault. So this is how dangerous that situation is. I would say this is the best recipe to a disaster. Now, okay, our case study. So that was just a little introduction about partial discharge and the slot PD that we tend to see in the generators. So we have an 11 kV, 1500 RPM, so small 4-pole machine. It's got daily starts and stops. It's got Rogowski coils installed on each phase. And periodically, this particular customer has measured PD and ozone. So bear in mind, there was no online system installed. Just every so often, the customer will go and measure PD and ozone. And this is what they found. These are the results from 2014 up to 2018. And you can see the column with PD value. And on the right-hand side, you can see the value of the ozone content. And what I want you to focus on is that the bottom here. What you see here is that jump between, in this case, 16 nanocoulombs up to 1.6 nanocoulombs up to 3.3 nanocoulombs. And the same happened with the ozone. What we didn't know, because that was just tests performed periodically, we don't know if that jump is just a gradual increase of PD value, or maybe that was already this exponential curve that we should be really worried about. This is something that we don't know. Unfortunately, a few months later, this machine suffered from an air fault. The customer was forced to send this stator to our Rugby factory in UK, and we had to not only perform stator rewinds, but also the core repair. And you can see here on the bottom picture an evidence of slot partial discharge, because for those who don't know, the surface of that stator bar should be dark, should be black, because the semiconductive tape or varnish in color is black, or basically like in here in this location. So these are the consequences. Let's look closely at what happened. There was an air fault at the slot exit, and you can see not only damaged coil at the slot exit, but also you see damaged core. So that repair was quite expensive, unfortunately. So this is what happens when you miss that spot, when you have slot partial discharge increasing over time. Now, let's go to example number 2. In this case, we have the machine of very similar rated voltage, 11.3, also 1500 RPM. Later, this machine had PD sensors installed and LiveView PDA2 permanent monitoring system installed, but that was later. So let's go step by step and see what has happened to that machine. So initially, the customer had problems with the rotor, not with the stator. So the decision was made to send the rotor to our Rugby factory in UK. During the inspection, when you removed the rotor, we found problems on the stator winding. What's interesting that the stator winding damage that we have seen was so severe that our engineers recommended not to run this machine again. Unfortunately, the technical side is very often taken over by the commercial side, and this customer was forced to put this machine back online. But because they knew that they have severe problems, at this point, they installed PD online monitoring system. And let's see what has happened. So just want to share some pictures and interesting findings that we've noticed during the first outage when the machine came to our factory only with the rotor problems. So what you see here is the visual inspection and the picture with the borescope. And you can see this is the core, and this is the side of the stator bar. And that's white location, it's the spark erosion seen on the stator bars. We also could perform something called darkroom test. What you do, you put the whole stator into a dark room, and with the camera, you try to detect visible partial discharge. And what you see here is two pictures overlapped. One picture taken during the day when there was light on, and then the other one taken when it was completely dark. And you can see here the evidence of partial discharge when you have connection between the stator bar and the core. So that's something called darkroom test. And then when you look closely into the location where the visible PD was present, you can see clear damage of the stator surface, pretty much in the location where previously, on the previous example, a refold occurred. What we also did during the first outage, obviously, we performed partial discharge measurements. And on the right-hand side, you can see the results we obtained. And on the left-hand side, it's the document written by Sigre that determines the location of the PD. And if you take these two and overlap, you can see the resemblance between the Sigre report and the PD, the real PD data that we obtained when we measured partial discharge on this machine. And this kind of shape of partial discharge pattern means that you have problems with the slot PD. Amazing how accurate PDA2 could be. So with having that in mind, so we have all that information, the customer was forced to put the machine back online. But as I said before, they also installed the monitoring system. And let's see what information and what data we managed to obtain. So have a look at this picture. Apologies, first of all, for the quality of this picture, but clearly this is the trend. These are the points, the training points of partial discharge on this machine. And one of the faces, marked here with color white, has seen a significant increase since the machine came back online. So what our engineers did, they took all the data and plotted a proper curve so you can analyze exactly step by step of what has happened. So let's look closely of what happened. So the machine came back online, and for a period of time, everything was stable. You can see a slight change in PD value when the load change went from 14 to 15 megawatts. Then also you can see a difference in PD value, that dip, when the load has changed from 15 to 14. But then clearly it came back again, and the value of PD kept increasing over time. Now let's move to the right-hand side of that picture. You can still see some influence of different components. So at some point, the cooling door was closed and the temperature has changed, and that also created some fluctuations in the PD value. But at some point, if you look here, the PD value went exponentially up. And that obviously creates a challenge, because now we are facing the moment when you need to make certain decisions. And before I explain of what has happened to that machine, I would like you to take part of pool number 2, because I want to show you something in a minute. But before that, if you could answer the question, how quickly PD trend could become dangerous? And there's 3 different answers: less than a month, less than a year, and the final answer is less than 3 years. And I'll give you some time to think about it. I can see still people voting, so let me wait 2 seconds more. Okay, let me publish the results. Now you should see the results on your screen. So half of you, around half of you, says less than a month. Then 33% said less than 1 year, and 11% said less than 3 years. All right. Okay, so guys, remember your answers, because now we'll see what has happened to that machine. Look at this. So these are the dates that you have seen on the bottom of that graph. So for a period when the machine came back online, for the period of 4 days, the PD value was stable. Then you have that slight increase in PD value, steady increase, and that took around 18 days. And then that steep exponential increase in PD, what you've seen on the screen, was only 5 days. So the whole period between the time when the machine came back online up to the point when the machine was stopped, it was only 28 days. Imagine that. 28 days. It's just amazing. So the 50% of you were right. So congrats for those who answered less than 1 month. On this occasion, the customer has made the decision to stop the unit before a complete breakdown occurred. So the machine was stopped, was sent to our rugby workshop, and this is what we found when we started to remove the stator coils. And what you see here is that extreme damage, that severe damage of the stator bar surface. Let me just remind you, the stator bar surface should be black, the color like this, and yet you see that rusty surface on the bar. And then the ladder effect. So these dark lines, if I asked you, do you know what these are? But for those who don't know, I'm sure that most of you do know, but for those who don't know, this is the location of that cooling slot on the core. So this is the color, the original color of the stator bar. And then the slot itself, you can see that rusty color. And again, just coming back to the basic chemistry, we know that when PD occurs, ozone also is appearing, and ozone will cause stator core to corrode much quicker. Therefore, you see that rusty color on the surface of the stator slot. Now, one more thing to add, because these were the 2 case studies that I wanted to share with you. But a few weeks ago, I went to our Swiss laboratory when the engineers tried to improve the algorithm and develop the PD2 system to monitor slot, well, partial discharge as a whole. And I asked those engineers, can you simulate slot PD in the lab? And they quickly said yes. And in just a few minutes, this is what they did. So they took one of the stator coils, old one, and they wrapped this aluminum foil. On the left-hand side, you can clearly see that the aluminum foil is tight. And on the right-hand side, you can see that the same aluminum foil is loose. It's not really touching the stator bar surface. And then obviously we tested for the presence of PD. And what you see here on the left-hand side is the PD test when the winding was tight in the slot. And then on the right-hand side, you can see exactly the same shape as we have seen in the SIGRE report that will represent PD in the slot section. So let's look closely. So loose slot, and then what we can see from measuring partial discharge is the slot discharge here. And the way how to recognize using our system that partial discharge is taking place in the slot section is that nearly 90 degrees PD line and that curve that you see here, similar to that seen in SIGRE report. So amazing how quickly in the lab you can represent slot PD. And this is just to share with you, this is what I recorded with my phone while we were there. So that's the setup. You have that stator core. You have two types of good and loose coil. This is simulation. Everything is connected to partial discharge sensors. And then the sensor, the signal from the sensor goes to live view PDA2, and you now see the results of a loose coil. Just amazing how quickly you can present loose coil simulation. So yeah, that's all. Okay, so let's go to the summary. And I want to start with that. There's another report, SIGRE report 213/2010, when number of generators in United States were analyzed. And if you read in that report, you can find that there are occasions where slot PD leads to a breakdown very quickly. And for example, there was a generator breakdown caused by slot PD just after 3.5 years since commissioning. So 3.5 years from brand new machine to a breakdown due to slot PD. This is how quickly it could progress. And then the report gives an example of 4 generators that had to go through a stator rewind just after 1,500 hours, which is equivalent of around 1.5 years since commissioning. So look how quickly PD could eat that insulation system in the slot section. And I want to finish this meeting with 2 questions. So question number 1, how many more breakdowns are needed to apply online monitoring? So we discussed that example at the beginning. So on commercial planes, the answer is obvious these days, 0. There's no breakdowns. You cannot have breakdown on the plane. Past catastrophes were used to improve today's plane design, and we know that these days planes are the safest means to travel. Now, would answer be the same if I asked the same question about generator? Well, unfortunately, no. Generators do break, generators do fail, and yet we don't have any monitoring systems installed. Somebody might ask, so why don't we hear about generator breakdowns unlike planes? Well, for a starter, it's much easier to hide a problem if it's under the turbine hole roof. Second reason is really commercial. Our station operators don't want to share bad news with the world, especially if the company is public and it's listed on the stock exchange market. Basically, you don't want to go out and say, well, we have a breakdown in our power station because the stock exchange will plummet if you give that news. And unfortunately, because of that, power station operators don't exchange technical problems with each other. And as a consequence, they often don't know what technical issues they might potentially fail. That's the interesting one. Question number 2 is rather simple. Can you miss the critical spot while measuring PD periodically? Basically, if you do it offline only. Where so you have given 2 examples. The first example showed the power station where PD was monitored periodically. And when I say monitor, I mean measured offline periodically every 9 up to 12 months. And you have seen that this has led to a machine breakdown in operation. And then we gave you another example with the machine with the installed monitoring system, where the decision was made before the machine broke. So it saved a lot of hassle, a lot of time, and a lot of money. So I want to leave you with that question. And then the final poll number 3, it's the last question I want to ask today. It is this question. It's rather commercial. Feel free to answer yes or no. So the question is, do you wish to be contacted by Quartzelec representative? So if you answer yes, probably one of us will give you a call or send you an email, and we can provide you with more information about partial discharge monitoring system. And if you say no, obviously we won't bother you, and that's about it. I'm gonna wait a few more minutes because I can see people voting. Okay, and if you don't mind, I won't be publishing these results of that poll. I will leave that for myself because it's a commercial question. And with that in mind, we can move on to the last slide, which is questions. Thank you.
Thank you, Wojciech. You'll be pleased to know that you gained the audience during the presentation, so it must have been very good, very interesting. We do have a lot of questions. I'm going to try and group them a little bit because some of the questions overlap each other. But one of the main questions would be, what partial discharge levels are acceptable? And what is a safe level of partial discharge? I think that's a good way to answer that question.
Right. So the answer is not as simple as you might think. So there's 2 ways to look at partial discharge, but there's only, to be honest, there's only one good way to do it. And you need to remember that every machine is unique. Every machine, even if it's a sister machine manufactured in the same time, in the same factory, will have different PD value. So the ideal situation is to monitor PD value from the beginning when the machine is online. So that's why it's so difficult to determine the right or wrong PD level. Having said that, because as a company we've tested hundreds, thousands of machines, we have a large database with different machines and with different PD values. So we roughly can say what is the good PD value and what is the bad or wrong PD value. But again, this depends on the type of the machine in operation. But please let me emphasize, PD is the unique feature of every generator, and the only good way to do it is to look at every machine individually.
Thank you. Okay, 2 more related questions. One is, on the PD trend, we show 3 different trend curves. Can you explain what they are? And the related question is, how can you analyze the PD spectrum?
Right. So to answer first question, you see three trends because we always measure partial discharge on every phase. That's why you have seen phase A, B, and C, or whatever you call your phases. So you will have three separate lines trending over time, and they will simply measure three phases simultaneously. And another, the second question is about the pattern. So first of all, I'm really sorry that you missed our previous webinar when we showed how to analyze these patterns. We base our basically how we analyze. We base that on the experience, but there are some papers, technical publications that will help you to do that. IEC is one, and the SIGRE document that you have seen today, it's another one that can help you to at least start your journey in interpreting PD. But maybe that's a good reason to look up for our webinars in the future, because we might repeat the webinar when we actually spoke about how to analyze PD pattern.
Thank you. Indeed, some people spend their entire career fantasizing about partial discharge. Eh? Okay, a question here. How much should be the frequency that you check PD on a generator that does not have permanent online monitoring?
So that's a tricky question, because based on what I just said, we can certainly say that if you do it periodically, it might not work. And I just gave you an example of the situation where it didn't work. Having said that, the standard industry practice for offline PD is to perform annual testing. So every year during your annual inspection, you would perform offline PD. Having said that, if you see a problem, visual problem, or if you see any change in PD value, I think this is the moment when you really should start considering installation of the permanent online monitoring system. Ideally, you should have it from the very beginning, but if you don't want to do it, try to measure it every 12 months. And then when you see a problem developing, go for an online system.
Thank you. Now, here's a very perceptive question. Do we have any statistics about generator winding failure that failed due to PD as a percentage of those that did and did not have the monitors fitted?
Unfortunately, I wish I had that data. I would have used that today for sure. Unfortunately, we don't have it. What we do have we have data which would come from different insurance companies. And sometimes the insurance companies would share data with public. And some of them talk about generators breakdown. And one of them was published a while ago. Don't remember the exact name and date, but what I do remember is that the graph showed that 63% of generator breakdown was caused by stator winding failure. It didn't really say what stator winding failure was, that PD or anything else. It just said that more than 50%, it actually said 63% was caused by stator winding failure. I hope I helped you a bit with that answer.
So we have a question about remedies. If you find partial discharge, what are the remedies other than tightening up the winding? So please see if you can elaborate on that.
Yeah, it's not an easy one, but I think the answer depends on where PD is. Because if PD is present somewhere in the end winding zone or at the slot exit where you have easy access, then as a company, we have repair procedures for such situations. I think the difficulty is when PD is taking place in the slot section, because the access is very poor, and sometimes to perform the right repair, you would need to remove the coils. But what we've seen in the past people doing as a temporary repair, we've seen people injecting semiconductive varnish between the stator core. It's not varnish, it's like a putty. It needs to be something dense between the, oh, sorry, I just need, one thing that I didn't do is to turn on my phone. That's embarrassing, sorry. So we've seen people putting putty between the stator bar and the core to recover that semiconductive property of the stator bar. So that's one of the things you could look at doing.
I think I would add to that cleaning, keeping the generator clean, making sure there's no tracking potential between bars and core. And we have also seen reversal of the phases, haven't we? If you get a particular PD pattern at the high voltage end of the phase, some customers can buy themselves some more time. But I think some of these repairs, they buy you more time. They don't change the fact that you're going to have to seriously look at the winding. A related question, is there any chance to protect the generator through the protection system because you have partial discharge? I think what the question means is, could you link a generator trip or reduce load in the event of high PD? I think from my point of view, I would answer to say that really PD is a slow changing effect. It's not like an earth fault occurring where you do need to have a trip linked to it. I don't know if you can add to that, Wojciech.
Yes, that's right. That's exactly that. You can't really use PD to trip the unit as you would when you have protection system installed. I mean, because it takes a while. You make that decision based on the data you measured when you have online monitoring system installed. I'm not sure if that was the right answer, or did I answer it correctly?
Yes, I think it is possible. I mean, certainly on our monitoring system, we have alarms, we have on-off alarms, which could be linked to an alarm on the DCS. Also, it could be linked to a trip signal on the DCS. So it is possible. I think it's not the most practical way to deal with PD.
Yes, yeah. So this is a valid point. So the system we have, I'm not sure how the others do that, but we would have yellow and red light. If you have a problem, it will warn you, but it won't trip the machine. So you will see the red line flashing, and this is where you need to look into the data and analyze it properly.
Ooh, there's lots of questions here which are not so much related to PD.
Okay.
Well, do we need to disassemble the generator to install the PD monitoring system?
Okay, good question. No, not really, because where you install the sensors, it's when you have the terminals. So all we need to have is the access to the stator terminals. You place one sensor per phase, and that's about it. So it's actually very easy, and you can do it. Most of the times we can do it in a day. Sometimes if it's a very tricky installation, you might need 2 days.
Is the PD severity different between 6 kV and 11 kV generators?
Yeah, very much so. So the PD is caused, I did mention that is the electrical field strength, which increases with voltage. So the more voltage you have, the more PD you'll have. You shouldn't be really worried about the machines below 6 kV, because we know that for the air-cooled machines, the trigger for PD to appear will be somewhere between 3 and 3.5 kV. But the higher the voltage, the rated voltage of your unit is, the bigger the problem you have. So yes, if you operate 11 or even 15, maybe 23 kV machine, yeah, look at PD, because it's happening.
Okay, thank you, Wojciech. The last question. Would a generator with lots of starts and stops suffer from more PD than one that runs base load?
Yeah, yes, we got that question quite a lot, especially these days when the operation regime has changed for so many power stations. And unfortunately, the answer is yes. it changes, because what you must remember that every time you start the machine, the temperature inside increases, say 20 degrees up to 120. Then every time you stop the machine, it goes down from 120 to 20. And every time you do that, things will be moving against each other because of the temperature change. And that alone will cause problems between the side of the stator bar and the core, something that we've discussed today, because the thermal expansion of the stator core will have different rate at the same temperature as, for example, the insulation system. So yes, if you operate the machine with large number of starts and stops, this is another reasons to be worried about.
Thank you very much. Okay, now we have had other questions. I think it's better that we deal with them directly to the questioner. They're quite detailed, some of them, and specific to one or two applications. So if you have asked a question and we haven't answered it now, we will be in touch if you have provided an email address, so don't worry.
Yeah.
Okay, so thank you, Wojciech. Thanks for answering those questions as best you can. And that really concludes the webinar for today. Many thank you to everybody who joined. I hope you found it very interesting. Please, if you want to get in touch about any generator or motor related questions, you can see the contact details we have there, and look out for future webinars that we shall be putting out in the near future. Thank you very much.
Absolutely. Absolutely. Thank you so much, guys, and hope to see you next time. Cheers.